Welcome everyone to another seminar of mathematics and higher energy physics. Today we have a familiar face, which is Artan Sheshmani. He already gave a talk under the same program, but today he is going to give the second talk. So for the people who doesn't know who is Artan Sheshmani, he is currently professor at a joint institute between Harvard University and MIT called IFI. And also he's a professor at BIMSA, which is a research institute part of Tsinghua University. So thank you very much for accepting our invitation today.
Thanks so much, Daniel. And let me close my video because I have only one device, and I will share my screen and then you start. All right, so since I already gave a talk on these super Gromov-Witten invariants, I think the reference for this session is the original first talk. So super Gromov-Witten invariants, as the title said, part 2. Reference of it is part 1. But I do a review, nevertheless. I'm not expecting, even I forget some of the things I said, so I will give a review a little bit. So recall that a map from C to X from a super Riemann surface. So I'm gonna write it super Riemann surface SR. Super Riemann surface SRS. So C to an almost Kähler manifold X with a symplectic form. So with symplectic form, let's call that form omega. Okay, symplectic 2 form, and almost complex structure. So we fix that almost and let's say compatible, actually compatible almost complex structure. The structure J, okay, is called J holomorphic. Yes, if this map phi satisfies some superversion, I'm gonna put in the parentheses satisfies, let's just write it like this, some superversion version of the Dirac equation. Okay, so really in the part 1 of the talk, we discussed about J holomorphic curves and counting of those things, and just in a very hand-wavy fashion. So those are maps from algebraic curves into an ambient variety, and you would like to actually count them. These are the ones we study in here are super curves. So if you look at the structure sheaf of these things, their structure sheaf has a module theoretic description locally as polynomials in both even and odd variables. And so you're trying to map a super object into a non-super almost Kähler variety. And the way this is basically a map from one to the other. Let us assume that the odd variables, of course, via the map can be paired with each other and can produce even functions. So it is possible to embed this thing into an even variety. Other than that, what makes it a super J holomorphic curve is actually this satisfaction of this Dirac equation. So del bar with respect to J of phi is actually defined as 1/2 of derivative of this map plus I times I tensor J d phi. And you would like this restricted to D to be equal to 0, where D was actually the distribution. So let me actually mention one of these things. So what here is I is defined, this I'm just reviewing, by the way, these I did define last time. I is an almost complex structure, the most complex structure on the domain curve C. So this is that compactability between the two complex structures. D is half of the tangent bundle of C. So D is a subspace of the tangent bundle of the curve C, which is called the distribution. So it's a distribution defining actually the super Riemann surface structure. Okay. All right. So that's what distribution was. And in the first talk, I invite you to go and see that I actually showed what exact sequences this D with respect to the tangent bundle of C to satisfy. And basically D is the half even part of the tangent bundle of C, because tangent bundle of C is also both odd and even. Okay, so that's the distribution. Here, so what we can actually show is the moduli space. So the let's just see. So we would like to moduli space. Let's call it the super moduli space, which we called it in the last talk X beta. So you're looking at a moduli space that sends these curves, super curves, into the ambient variety, and you would like to look at homology theory of the reduced part of the curve. The reduced part of the curve is the even part of the curve, and after embedding into the ambient, almost scalar variety, you would like that to be having a fixed homology class, because you would like to count these things up to homology. So this homology class beta is actually like a degree of freedom for you. So you kind of change it, and then you count how many of these you have, and then you move on and you change beta again and keep going like that. So each time that you fix beta, you have a moduli space. And moduli space itself is a super moduli space. It's also even and odd, obviously. It's parameterizing odd and even objects. And we actually showed that this is the zero locus of this d bar j actually operator. So that's what it is. So the way this d bar j operator was that this d bar j operator. Okay, so it's the zero locus of this d bar j. So you can actually ask yourself, what is d bar j phi really? It looks like derivative of sections of a bundle. So you look at your space that parameterizes all of these curves embedded inside your ambient variety, and then there is a bundle whose fibers are going to be given realization of, whose fibers need to have this kind of description. And then the zero locus, because d bar j of phi is vanishing, the zero locus of a section of this bundle would be your moduli space. So you're not interested in all super curves embedded in the ambient variety, but you're interested in the ones that satisfy this differential equation. So this is a section, and this section comes and intersects the zero section of this bundle. So let's say I call this bundle E, for instance. And this is a very kind of intuitive picture. It's not that the zero locus of this section needs to necessarily be points. So it's not true. It could be that this section intersects in a non-isolated manner like that. And you would like to actually count how many of these things are. Essentially, every point, because if this is your moduli space of all possible maps from C to X, then basically the ones which you are interested in, the J-holomorphic ones, are basically only these points of intersection or loci of intersection. So if they are isolated, you would like to count them. And if they are not isolated, you would like to do some kind of excess intersection theory calculation, meaning that if you have a locus like this, you use intersection theory and virtually think about some kind of a normal shift to that locus. And instead of intersecting the section itself, which is non-transverse, you intersect that normal sheaf actually with the base, and you will get a number. Okay, and then you add that number to the rest, and that will be invariant of your deformation theory problem, a moduli problem. Okay, so as soon as you fix the variety and you fix the homology class beta, you get this bundle. Okay, you get this bundle. This bundle is everywhere, and you get this section. And then the zero locus of this section is the moduli space of J holomorphic curves. Okay, so here, I said this bundle. So fiber of this bundle, the fiber E, restricted to a point of the moduli space. So this is a super curve mapped to X. That's a point. That's a point of the moduli space, right? Point of this moduli space of all maps, all maps from super curves into the ambient non-super variety. This thing is actually a space of sections of the dual of this distribution, the even half part of the tangent bundle, tensor with pullback of the tangent bundle of the variety X. Okay, tensor with O of C, basically something like that. Okay, so it's essentially, basically, this fiber will actually see kind of deformation of the ambient variety and deformation of the target domain. So you would like to map these curves, right? You would like to do a certain deformation theory problem. You would like to be able to compute a very nice deformation invariant, which is invariant with respect to deforming the map or deforming the domain of the map, as well as the target of the map. Okay, infinitesimally. So here is a theorem that I mentioned last time. So there was a theorem as we discussed in the joint work with my former postdoc, Enno Kähler. Everything I say here is joined with Kähler and Professor Yao. In 2022, we saw that under certain conditions, on C and this variety X, the moduli space MX beta of maps from C to X such that push forward of the reduced part of the homology class of the reduced part of the curve is equal to beta, and this beta you would like to be an element of second integral homology of the variety. Okay, is in this situation, this moduli space of maps is a real super manifold of dimension. So the real dimension of this thing, because it's a super manifold, the dimension of a super manifold has an odd part and an even part. So this will be the dimension of complex dimension of X times 2 plus 2 times integral of C1 of tangent bundle of X integrated against homology class beta. And the odd part of it, so this is the even part, and the odd dimension of it is 2 times C1 of tangent bundle of X beta. Okay, so this kind of calculation as actually you can do several different ways of seeing this calculation. So some calculations like Grothendieck-Riemann rock, but the super version of it actually can show you what is the dimension of this loci, which you obtain by looking at the zero section bundle. Okay, that's one kind of calculation you can do. The other calculation is actually index theorem. So you can use differential geometry to actually, and index theory actually, to calculate this dimension of the moduli space. Okay, so roughly speaking, if I look at roughly speaking, S of x beta, which is given by the zero locus of S, and S is a section of where S is a section of this bundle E, satisfying, and ds is a map from tangent bundle of H, we called it, to pullback of tangent bundle of E. So this is the tangent bundle to the moduli space of all possible maps. Tangent bundle to
Yeah, I think
moduli.
there is a question.
Yeah. Mm-hmm.
Yes.
Yeah,
Hi,
go.
thank you. Yes, I have a question. Here, do we also impose the stability condition for this modular space of maps from the curve to X?
Good question. Yes. So at this point, everything I'm saying is about the interior of this moduli space. So curves are always smooth. Of course, the stability condition appears when you would like to see how far this curve can deform. And for us, the stability condition is that because we don't want to overcount things infinitely many times, the stability condition for us is that this curve we would like to have finite automorphisms. And when the curve deforms, we would like to kind of limit the possible copies of the curve. So that's what the stability condition do. So in the interior of the moduli space, the stability condition kind of is trivial. I mean, the smooth curves are stable. But then, of course, you need to because your moduli space is non-compact that way, and you need to compactify this moduli space. So stability condition somewhat actually tells you how singular your curves can be if they are non-smooth. And both in the reduced case where you are not counting supercurves, but just reduced honest curves, like in Gromov-Witten theory, and in here, you actually use the similar stability condition when you compactify this space. Right now, I'm just telling you interior of the moduli space. So yes, the answer is yes, the stability condition we will use when we would like to compactify and then define invariance over this compacted space, integrals over this compacted space. Okay.
Okay, thank you. So far, this moduli space is non-compact, right?
Non-compact, exactly, non-compact.
Okay.
Okay, so this
Thank
thing, sure. And then, so this H is the tangent, this TH is the tangent. Okay, so I think I didn't give it a name in here, but maybe I should delete this. This basis space I am looking at in here is H. This is the space of all possible maps, the space of all maps, not the J-holomorphic ones, but all maps. This thing, the whole thing would be your moduli space. The moduli space sits inside H. And how does it sit? It sits as the zero section of this S, and this is S. This is this S. Okay, so that's the picture. And so the S is actually a map from TH to this bundle. So this bundle, I gave you what fiber-wise this bundle looks like. So you look at D of S, and you can actually immediately see that, okay, and zero locus of S sits inside H, right? And that's our moduli space. And so you will actually, we obtain an exact sequence. Oops. Why is my laptop? Okay, an exact sequence. And this is basically like this. So 0 goes to, okay, so let me, embedding of the moduli space inside the space of all possible maps, not just the super J holomorphic ones, but all super maps. I call it I. Pullback of kernel of ds gets mapped to pullback of tangent bundle of this ambient space of all possible super maps. pullback of tangent bundle of the bundle E, and then pullback of co-kernel ds. Basically, this is an exact sequence that you get. And what this is the space of deformation. So this is deformation space. Deformation space of J holomorphic, super J holomorphic curves. Holomorphic curves. This is the obstruction space. Obstruction space of super, not all curves, but super J holomorphic curves. Okay, so we actually, it's been working progress for us for 3-4 years now, because really, even the notion of super J holomorphic curve, I don't think existed. So we needed to develop these things, mimicking really the reduced theory. Okay, now, of course, there is an object in the derived category of this whole moduli space of all maps with cohomologies given by these two. Okay, which are capturing sheaves whose fibers are exactly deformations of J holomorphic curves and obstructions to deformations of J holomorphic curves. This object I will, if I have time, I will define later. Okay, so derived categorical description, the one that gives you deformation obstruction theory, I can define later. Now, to go back to this moduli space for a super point, because our moduli space is a even an odd space, points in this moduli space will be also even and odd points. So super point means something like this. So it's a point over real numbers, for instance, but it can have some dimensions. So you can think of a point together with some jet of functions actually attached to it, and those are odd functions. So when we say point in the supergeometry, it means the reduced part of it is a point, but it could have some vector space of odd functions attached to it. When we say a line, same thing. When we say a curve, it means that reduced part of it is a curve, but you can have a kind of sheaf of odd functions attached to this even curve. Okay, so for a super point, the p points of this space, okay, are pairs like phi and psi, such that phi is a map from C reduced times point to X, satisfying some kind of inhomogeneous del bar J equation, so satisfying an inhomogeneous del bar J differential equation. Okay, and here basically, and the section here, this is that your map phi and psi is a section. So psi is an element of the global sections of, I'm going to call it S tensor over C times pullback of the tangent bundle of X of the twisted spinor bundle. So this is the twisted spinor bundle on the curve, on the super curve. So what is the spinor bundle? Well, you know about the canonical bundle. The spinor bundle is the one which pairs to canonical bundle. It pairs with itself, and the second full tensor product of the spinor bundle should be isomorphic to canonical bundle. Now, this is something important from technical point of view. If you are actually already expert in this field or in this particular topic, it's not always true that square root of a bundle is well defined. So for instance, you can have, say, P1, canonical bundle of P1 is anti-Neff bundle. It is O minus 2 over P1, and the square root of that would be O minus 1. Actually, this should be something like that, dual of that. Well, okay, so it is here definable. So for instance, if C is a super P1, like P11, then the spinor bundle actually on the super P11 would be just the square root of the dual of the canonical bundle. So it would be basically this. Okay, but it's not always true that this is the case. Obviously, you cannot always have this kind of a bundle. Taking the square roots is not always possible. So when that comes, then you kind of need to view these curves not in the space that parameterizes these things, but as in some kind of a root stack. So whatever root stack means, I'm not going to get into it, but you should take root stack of your space, like the second root stack of your space. That's the space that parameterizes these kind of shadow of these objects in some sense. And over there, the spinor bundle would be definable. This is the situation where the degree of the spinor bundle will have to be half integer. So taking first Chern class of something, and that's the degree of bundle, being half integer doesn't make sense. But over the root stack, you kind of lift your bundles, and over there, you will calculate integers for the lift of your bundles as a degree of bundles, but those integers are reminiscent of half integer kind of spinor classes. Okay, so just keyword if you want to keep in mind is that over root stacks, spinor bundles are always defined. Okay, but I don't want to really get into it because it's some technical thing and it kind of deviates you from the main storyline of this. Okay, so let's just, yeah. And what is this spinor bundle anyway, measuring? The spinor bundle is a normal bundle to the reduced part of the curve relative to the ambient curve. Okay, so for instance, for C super V even and odd P1, P11 is embedded, the reduced part of this thing is embedded obviously into this. Okay, and the spinor bundle, which is isomorphic to OP1 of 1, it's a bundle on the reduced thing. It has sections, and those sections actually tell you how odd the ambient super curve is. So a spinor bundle actually is isomorphic to normal bundle of P1 inside P1. Okay, so that's what it is. All right. It follows that the reduced manifold mx beta reduced is the moduli space of just regular or reduced J-holomorphic curves. These J-holomorphic curves, phi reduced maps these reduced part of the curve into the ambient variety, and the reduced moduli space actually sits inside the super moduli space. The reduced moduli space parameterizes J-holomorphic maps from reduced curves into the ambient almost Kähler variety, and the super one parameterizes embedding of super curves into the ambient non-super variety. Okay, with the normal bundle, okay, similar to before. I just told you what point-wise calculation is over a point. Let's say you're looking at genus 0 super curves. This is all you need to know to understand really the story, I would claim. Okay, and you just generalizing things to the notion of family is just very easy. So okay, so you have the normal bundle m reduced x beta to inside the super x beta. Okay, and this normal bundle is a bundle over the n reduced, right? So m reduced X beta. It's a vector bundle. Okay. So what is this? So given a point, because it's a bundle over the space that parameterizes this space, every point in this space is a reduced curve being mapped into the ambient variety. Every point in this space is like that. So I can look at the fiber of this normal bundle on that. So the over a point in the space downstairs, like this, which is a point in this here. Okay. You can see that the fiber of n m reduced inside m super is equal to fiber over this point. Let's call it something, point P. Okay, is equal to holomorphic sections of this thing. So spinor bundle again, twisted spinor bundle of the twisted spinor bundle. So let me continue in the next page. I hope this is okay.
I have a question. I have a very nice question.
Yeah.
Why do you consider the twisted spinor bundle instead of just the usual one?
You're twisting it by the pullback of the tangent bundle of X. And the reason you're doing it is that you don't just care about deforming the curve, you're caring about deforming the curve and the map. So this pullback of the tangent bundle, if you think about it, right? If you have the map phi, C goes to X. D phi takes tangent bundle of C to tangent bundle of X, right? So the discrepancy between them is actually deformation of the map. So when you put pullback of the tangent bundle of X, that actually sees deformation of the map, really. Okay, so that's why you're twisting things by that. You're not just deforming your curve, you're deforming the curve and the map.
Oh, okay, thank you.
Okay, you're twisting it by that pullback. Okay, so that's the twisted spinor bundle over the super Riemann surface. Super Riemann surface C reduced. Now we come to this question that you asked. Here is a remark. It is well known. It is well known that this reduced space, the space of maps, only maps from curves, reduced curves to an ambient variety, is not compact and has a compactification. Okay, so this thing X beta sits inside this compactified version like that, and that is basically Konsevich's space. Space of the stable maps. That's the reduced thing for us. Okay, and what we've showed in a theorem. Okay, 2020, we showed that when I asked my super curve to be only genus 01. This is the only genus 0 possible super curve, by the way, with super Riemann surface structure. Then the moduli space of super stable maps is defined as well, you know, obviously you know very well that moduli spaces are spaces representing moduli functors. So there is a moduli functor. So these are genus 0 things. Usual to Gromov-Witten theory, you can fix some number of mark points on it. Those keep track of where the curve conhot becomes, analytically speaking, becomes singular. And so you would like to kind of satisfy some finite length geodesic condition over the, okay, I'm not going to get into it because also in the first video I talked about it. But so this thing is a moduli functor that takes you from the category of superpoints, opposite category of superpoints, to the category of topological spaces. From opposite category of superpoints, to the category of topological spaces, to topological spaces. Okay, and basically this space, again, this space, if I take this super moduli space functor and I pick a super point, let's say R00, all moduli functors are two categories fibered over categories. This is also a two category. It's a two category because morphisms between objects that the moduli space parameterize, this you want to be isomorphisms. And so this is a category, and I can look at the fiber of this functor over an element of that category, which is something like this. And this is exactly the M0 and X beta, the canonical classical space of stable maps with n mark points. So you see how you view these supermoduli spaces. Now that you have constructed the superfunctor, when you restrict to the element of the category that doesn't have any odd function here, that basically tells you that as soon as you evaluate over this particular element, you strip off all the odd information. And nevertheless, you actually get a whole classical space of regular stable maps. Okay. So the superspace is when you identify, when you look at the fiber of this functor on superpoints. Okay. Yeah.
It shouldn't be a spectrum of C instead of these are, I don't understand the notation. These are.
Yeah, so when we were actually constructing this moduli space, we were constructing it as a super manifold. But yes, actually you can do everything over, or super real manifold, but you can do everything over complex. Yeah.
But this notation is the spectrum of over the
exactly.
reals.
This is the spectrum of Z. This is the spectrum of Z, for instance. So 1 point.
Okay. Okay.
Yeah. Yeah. Okay. So one other thing is that I mentioned briefly last time that okay, one thing you can do is you can specialize. We can specialize the super stable maps to those with given fixed tree type. So you know there is a combinatorial way of putting labels on stable maps. For instance, you can have a curve which is, let's say, higher genus or even genus 0. So it's a bunch of P1s, for instance. So it can be P1s, you know, topologically speaking. I mean, these are like things, genus 0, these are spheres, right? So you can have things like this attached to each other. And, you know, some of them might actually become singular, things like that. Okay, so this is actually a point of singularity, this is a point of singularity. Okay, you can have these things. So there are graphs There is a graph theoretic description of this. And when you fix the graph theoretic label, it actually tells you what kind of configuration of curves you're looking at. And then these actually cut out for you loci of the ambient moduli space, in which these curves can, of course, still form in different ways, but this graph theoretic label of them will not change. This configuration of them, let's say, including how many genus zero components and how many, these will not actually change, okay? So you can fix this graph. So these are P1s, for instance, for us, P11s, and so that's why they are not having any holes and so on, so they look like trees, actually. Okay, so fixed tree type T and distribution of homology class beta. So if your whole curve as a whole has class beta, then you can basically tell me how much of this beta is distributed where. Okay, so this beta, it's a graph, and then to each vertex of the graph, you can associate a part of beta, subclass of beta. It goes like up to number of vertices. So these are the set of vertices of the graph, vertices of the tree. And this will be basically going all the way to how many vertices you actually have in that tree. Okay, class over vertices of T. So this actually is a way of fixing topological information of this image of the curve after being embedded into the ambient variety. So when you do that, actually, you realize that then we see that there exists a torus action, C star, okay, acting on the supermoduli space of genus zero supercurves embedded into the ambient variety with the fixed topological type. So instead of fixing the homology class beta, now I fix the vector of homology classes associated to my tree, okay? And there is a torus acting on this thing. Something like that, okay? And this torus and this C star action has a fixed locus, given by the substack M bar compactified line. Everything in here is, by the way, compactified. Now I allow singular curves. Already I show you a picture over there is a singular thing, right? It's some things like this, right? These are singular, right? Okay, so this one actually has a fixed locus, which is our regular Concevich's moduli space, like that. So what is really the idea? The idea is that you have the regular Concevich's moduli space of stable maps, and you would like to kind of take advantage of that moduli space, okay? You have this ambient supermoduli stack, so you realize that you can cook up the problem in a nice way that you can investigate existence of such torus action. And then fixed locus of this torus is the regular Concevich's space. So then there you can use torus localization to do calculations, okay? So that's the idea. So let me put it all in words. So definition of super Gromov-Witten invariants. Okay, so how do you do that? In order to define the super GW invariance, one needs to consider construction construction of this m bar 0 and x beta super as a de Montfort superstack. You can have constructions of superstack and then construct. Well, we would like to do equivariant cohomology theory. That's what localization is. So we would like to construct supergeometric version of equivariant cohomology theory.
Yes, I would like to ask about the localization. What kind of localization
well,
does it fit better here?
If you have, this is porous
or...
localization. So let's say you have a manifold, okay? Let's say you have a manifold, and let's say you have an action of a group on this manifold. This is a group, okay? So this group action is realized as a map from G times M to M. Let's say this group action has an invariant locus. So it's a part of the manifold which doesn't move with action of the elements of the group acting on the points on that manifold. So those are the loci or invariant parts, right? So let's say you have invariant parts, loci, Z1, Z2, so on, up to Zn. And these things are G invariant loci inside this manifold, okay? Now here is what Atiyah and Bott actually proved, that if you have such a thing, then you can actually see that the fundamental class of your manifold is an element of homology theory of your manifold. It's a homology class, right? Then the fundamental class can actually be recovered from the fundamental class of these loci Z1, Z2, Zn. Okay, so it would be fundamental class of Z1, and it will see fundamental class of Z2, and it will see fundamental class of Zn. And you're adding classes inside homology theory. So for us, this homology would be actually Cha homology. And you cannot just agree that this is the case. Of course, you need to do modifications. So basically what is happening is that you divide these classes by Euler class of something. And that something, I'm going to call it normal bundle N1, normal bundle N2, and it keeps normal bundle N3. So you realize that these torus or these G-fixed invariant or G-fixed loci inside M actually have normal bundles, N1, N2, and Nn. So in Euler class of these things are elements of cohomology theory of these loci. And cohomology or homology theory of these loci embeds inside ambient homology theory of M. So this is actually Atiyah-Bott localization theorem that is extremely important because somehow this thing later actually shows how you can do intersection theory over non-compacted spaces. So it could be that you want to define some kind of an integral. So in our thing, so if you wanted to actually calculate Euler characteristic of this manifold, right? Euler characteristic of this very manifold in this picture, this would be integral over M of top Chern class, right? Of the tangent bundle of your manifold, for instance, with the sign. This is what differential topology tells you. In terms of intersection cohomology theory is actually a collapsing of a cohomology class with the homology class. So it's actually this intersected with fundamental class of your M. So you see, when you have that thing, you can see that Euler characteristic of M can actually be written as C top of M, Pm, intersected with this sum. So all you need to understand is the homology class of these fixed loci, and you need to understand normal bundle to them, okay? And then there's just the homology or cohomology theory calculation, intersection theory calculation. Now, in our line of the problems we are discussing, it's not that easy because your space is not a smooth manifold, unfortunately. Your space is often some kind of a very ill-defined, ill-shaped, multi-component space. Its dimension of components jumps around. So there, you actually artificially construct some cycle associated to this space. And this cycle only realizes the space sitting in the correct expected dimension. This cycle actually is the virtual fundamental cycle. So in our calculations, we cannot just, if you calculate this, because the space has so many components, this integral will jump in dimension, cannot be a number, cannot be an invariant. Whereas in manifolds theory, Euler characteristic, I mean, there is no more sophisticated invariant than the Euler characteristic. Not only is deformation invariant, it's actually topological invariant. But for us, we don't even have deformation invariant. So what you do, you actually do this calculation over, okay, so I cannot write really, if I am very pedantic, I don't want to write it as an integral, but it's like I use this part. So it's a C top of something, okay, and then something. And this something will be the virtual fundamental class. The virtual fundamental class sits inside Cha homology of Eurospace. Now remember that Eurospace is like a moduli space. It's really ill-shaped. So that's a Cha homology class. And what is this thing? Well, it's not tangent bundle, because if Eurospace is union of point and a line, for instance, what is the tangent? The tangent sheaf at some point will be zero-dimensional, because that's the point. Point is zero-dimensional. This tangent is zero-dimensional. Some point is a line, so it's one-dimensional. So this tangent thing actually jumps around. It's a sheaf, but it's not a bundle. But then you can construct using intersection theory something, and that's the obstruction bundle. Okay? So if you actually kind of reformulate this calculation into this kind of formalism, somewhat virtually, algebraically speaking, you construct some invariant that following the construction remains invariant under infinitesimal deformations of M, okay? And there, again, you can use localization. So if you have a virtual version of localization, so if you have a virtual version, meaning localization for a virtual class, virtual version of localization, okay? Then you can replace this with the sum of the virtual class of the G-fixed loci. And again, these will need to be very much well-behaved and well-defined. So normal sheaf to these things cannot jump in dimensions, okay? And this virtual version of the localization was worked out by Pandripante and Graeber and Pandripante. And Graeber was his postdoc. Okay, so it's because of work of these people that we actually can use this technology, really. Okay, did I answer your question? So this is actually what we are doing. So we would like to take advantage of work of these amazing people. We have this supermoduli stack, and we realize we worked very, very hard to actually find this torus. To find a compatible torus that actually has all of these properties was not really easy. Okay, so I can say one paper that we wrote, with the title is Torus Action on this moduli space. Recently, I put it up, or maybe Enno did. This paper is all about defining this suitable torus, actually, that realizes the Kontsevich space as a fixed locus inside this ambient superstack. Okay, so that's what we are doing. Now, one thing I mentioned here is that, you see, in order to do this localization theory and this, you need to actually, okay, so when you do localization here, elements, the classes that you use in here are kind of equivariant classes. So these are G equivariant homology classes. So in order to use this technology of Atiyah-Bat, or the virtual version of it, Graeber-Pandripante, you actually need to already have equivariant cohomology theory for your moduli stack. Now, if your moduli stack is a Deligne-Mumford stack, you have it. But if it's the super Deligne-Mumford stack, that itself was not developed when we already had this idea of doing this. So we were kind of in a lot of pain because we didn't know what to do. Like, how can you use a formula where the very element that is on the left-hand side of this formula itself is not defined? Okay, but thankfully, actually, it got defined. So, So in order to, where was a super geometric version of the equivariant cohomology theory, I continue here, okay? So equivariant cohomology theory, so this is the super equivariant cohomology of the super stack of the stable maps. Okay, but okay, so this is somewhat work in progress, actually, in the community. Somewhat work in progress. Okay, so people who have actually worked on this thing and defined it are, there's a paper by Barbuto, Manin, may he rest in peace, Professor Manin, and Hernandez Rupires. Okay, so they are actually, they defined in some special cases supergeometric child group. Supergeometric child group. You see, as I said, these homologies are Chow homology, and Chow group, the super version of Chow group, was not defined actually originally. But then, as we already kind of tried to be very sloppy, and we said, okay, let's say the left-hand side of this star, let me call it the star, this one. Let's just say, okay, for the super version of it. So if I put this thing here, this is what we want to do, right? So this is star equation we didn't have. And we said, let's assume we have it. And let's just see what we get if we have it. Okay, computations still can be carried out. But we got lucky, and then these people actually defined it, and their setup actually fits our setup. So it's basically given by them. Something that they did is that if you have a moduli space parameterizing objects where odd functions are only, there is a one-dimensional vector space of odd functions, let's say similar to the P11s I mentioned to you. So this, if this guy is 1, then that super Chow group is actually defined. But if there are more variables, meaning that the odd dimensions are more, like 3, 4, 5, 6, then it is not well defined yet. But for us, we are looking at most canonical genus 0 P11s getting mapped into the almost Kähler variety, so it fits our picture. So we didn't need to work hard. We just used the fact that they have defined it already rigorously. Okay, so then we can define the super Gromov-Witten invariants via torus localization, via virtual torus localization. Via virtual, now you know what virtual is. It's an identification of virtual class of the space with fixed loci, and I'm gonna call it torus because our group scheme here that's acting on our stack is a torus. Okay, so via virtual localization, via virtual torus localization. Okay, now consider the following commutative diagram. Okay, so what is the story? Summary of everything I showed so far told you is that there is a compactification, the super stack of super stable maps, right? And then sits inside it the reduced Konsevich's stack of the stable maps. That's also a compactified thing. And then this guy gets mapped to x of n, x to the n. Our curves are being mapped with n mark points on them. If you just tell me inside x, which locations these mark points will be sent to, that gives you a map from your moduli space. As soon as you give me information of some curve with n mark points on it, together with a map that sends curve to x, this thing can get mapped to location of these markings, and that's an n tuple. And that's a tuple which belongs to n-fold product of x. So obviously you have this well-defined map. So this is the evaluation map, it's called, okay? And all right, so there is an evaluation map from super moduli space to X of n, and then there is a evaluation map from the reduced moduli space, and the reduced space sits inside super space. Yes. There is another thing too, which is, well, I can think about parameterizing maps from curves to X, or I can just forget the map. I can forget this phi part. So this, forgetting phi. So this I'm gonna call it pi, forgetting phi. So that's the super moduli space, which is itself actually well defined, of just parameterizing super curves, regardless of getting mapped to X with homology, fixed homology class. Okay, and obviously in the reduced version of this also this exists. So there is a pi reduced from this to the moduli space of super curves. So this is the super stack of stable curves, rather. Stable curves. And that middle one is the super stack of stable maps. And you obviously have the reduced version of these things, and the reduced components also sits inside the super component, super stacks. Okay. Okay. Now assuming equivariant super cohomology theory of this stack and this stack, the super stack of curves, just like that, are defined, are well defined, which, as I said, under certain conditions are well defined. Depends on how much odd freedom you allow the curve to be. If you limit it to one variable or one dimensional or two dimensional, that's okay. But higher than that, it's not okay. Okay. So this is well defined, and then the super Gromov-Witten invariant then can be actually defined as the following. So if you have super Gromov-Witten invariant of curves mapping to X with homology class beta, and you evaluate this thing at alpha 1 to alpha n, is going to be integral of pullback of alpha 1 times alpha n integrated over the super stack. Now you might ask, sorry, I didn't understand. Where is alpha? What is happening? Well, what is happening is that you're trying to send by your map phi, this curve with the markings P1 to Pn into your ambient variety. Over there, you would like to completely keep track of where the curve lands. So let's say you have a cycle in here, which is Z1, some cycle in here, and they have some cycle. Okay, in order to not to confuse, I called them Z before. Let me call this thing something else. Some cycle D1, and then some cycle D2, and all the way, say, Dn. Yes? So these are cycles inside ambient X. So what you want to do really, ideally you're interested in mapping the curve so that when it goes to X, it kind of has intersection. Oops, what happened? It became discretized. Okay, intersection with these cycles. Okay, so what you do basically is that you realize that each one of the cycle has a homology class. It's a fundamental class. It's a smooth variety after all. Poincare dual of this homology class is alpha I. So if you actually look at the tensor product of alpha 1 to alpha n, as in down here, and via the evaluation map, so this thing alpha 1 times tensor product over here lives inside cohomology theory of n-fold product of X. If you pull it back via evaluation map to here and you integrate it over your moduli space, it is essentially basically by construction of the moduli space tells you you're not interested in all the curves that just roam around inside X, but you're interested in the ones that have n markings on them, and you would like the markings to land exactly on those cycles whose Poincare dual of homology class is alpha. Okay, so this is basically what it is. Everything I said in here for Kontsevich existed, and he defined it that way. Okay, so that's the normal Gromov-Witten theory. But for us, the only difference in here is that we needed to kind of define the super version of everything. Okay, so that's what it is. Now,
I have a basic question. I don't know if you can help me to understand it better, like how it is related. How does the counting of corps is related with the intersection points?
With the intersection point of what?
Yes. Yes, like the intersection problem and the enumerative problem, how are they related?
How is it the count of curves is related to anything about intersection?
Yes,
that's what
exactly.
You were asking.
Yes, because
Well,
that confuses me a lot because as far as I know, the Gromov-Witten invariants are to count the number of curves, but then they are also related to the problem of intersection of the same curves and divisors.
yeah.
Or I don't know. Well,
You see, this is the moduli space of curves, and I'm not talking about superversion. This is the moduli space of curves embedded into the variety, right? There is a bundle, obstruction bundle, on this moduli. As I said, if the moduli space is ill-defined, it's a stack with so many components, with singularities and so on. The tangent sheaf of this space cannot be a bundle. It jumps in dimension. But if you can come up with something, which something I wouldn't call it obstruction bundle, yes, and this bundle doesn't jump on dimension. So somehow, one thing it is like if the deformation is space at every point, deformation is space of points that the moduli space parameterize kind of jumps in dimension. The first order obstructions to those things is also jumping dimension. But you can make the obstruction a little bit bigger. You add a bit more functions, roughly speaking, such that you kind of obtain a bigger bundle that has this jumping dimension obstruction bundle in it. Okay, and this bigger bundle actually something which is algebraically speaking locally constant and also globally constant. So basically, it's a vector bundle. Okay, so this obstruction bundle is a bundle, and over every point of this bundle, fibers of it gives you vector spaces worth of obstruction space to deform the base point. Okay, so this is the point P. I would ask myself, what is the deformation space of this P if I allow X, for instance, to deform, or the map to deform? What is this point? This point P is a configuration of curve being mapped to X, basically. That's what the point means in this particular moduli space. So deformation of P amounts to deforming the map or deforming the domain curve and deforming basically everything, right? Okay, what's the deformation space? Well, depending on where I go around by P, it jumps in dimension. But maybe there is an obstruction bundle which has a bit, first of all, it's fiber-wise over every point of the moduli space gives me obstruction, first order obstructions to deforming this P. Basically, it measures to me how far am I for my deformation space to be a bundle. So the obstruction space actually measures that for you. Okay. And there is a suitable choice of obstruction sheaf, which actually happens to be a bundle, and it has this intrinsic obstruction sheaf inside it. So this obstruction sheaf also actually tells you what is the fiber-wise, what's the vector space of obstructions to deforming that point. Okay. Now, what is the connection between all of this story and this word intersection? That's what you want to know. You are hearing the word intersection. You want to know what is going on. Okay, so this obstruction bundle actually has a section. And the section is meeting like this. So you are interested in deformation invariant curves mapped to X. I ask you, if S is a section of obstruction, and you know that on those places that the point in the base deforms nicely, obstruction should vanish. Can you tell me how many of these points down? Where are they? What should I look at? You should look at zero locus of this section, right? Basically, this is the zero locus. Do you agree? You're interested in deformation invariants. So these things that have nice flat deformations. So those should land on the part of the basis space because they are still giving you curves. What curves? The curves which deform nicely. The curves that the fiber of the obstruction bundle over that curve, the section of the obstruction bundle, evaluated at those points vanishes. Obstructions vanish. So basically, you're intersecting this section with the base moduli space. So count of curves that deform nicely inside X is in fact intersection number of this S with your base.
Okay, and they correspond to the zero locus, right?
Correct.
Okay. Thank you.
Right. Oh, okay, yeah. So that's what it is. After all, it's an intersection. Okay. Even in the smooth case, where an invariant Euler characteristic of a manifold is given by minus C1 of tangent bundle of that manifold integrated over M, which is really fundamental cycle of the manifold intersected with this tangent, this Furtian class, this cohomology class of top degree. Yes. Even there, right? Tops, not C1, C top. Sorry, C top. This is the Euler class. Yes, C top. Okay, even there, you have your base manifold. And here, the obstruction bundle is not needed. Actually, your tangent sheaf is a bundle, so you have the tangent bundle. And what is this top Chern class or Euler class? If you Wikipedia it, you will see that it's the class of the vanishing locus of a canonical section of this tangent bundle. So it's some kind of it's the class, it's the cohomology class of the locus of the vanishing of this. If this is a S, this locus is zero locus of S. And it has a cohomology theory inside M, and it is actually equal to this one. You see? That's what it is. So when you take the Euler class of tangent bundle, indeed, also, there also you're intersecting section of some bundle over your space to calculate some invariant for a space, right? But there the bundle is actually tangent bundle. Okay, so I hope I answered your question. All right, so now where was I? So we have this integral over the super stack. Now restricting the super stable maps of fixed type given by T. As I said, I want to keep kind of fix the combinatorial label associated to my curves, configuration of how many P1s, how they are meeting, so on. Then as soon as we do that, we use the torus, T. There's a torus acting on this moduli space, super stack of nx beta associated to the fixed tree, and okay, x beta associated to the fixed tree, like that, whose fixed locus is given by m reduced 0n x beta vt. You see, fixed locus is the Konsevich's reduced or conservative regular stable maps from reduced curves into ambient variety X with fixed tree configuration of trees. Okay, so then basically all you need to do, you kind of do the following. So you can relate. We can define a localization map. So localization means you want to do kind of things like this. So you want to take these homology classes and divide them or invert some cohomology classes. Those are the ones that come in the denominator, and you basically cup them with each other, right? You can basically take homology class, Euler class of N1 minus, and you're capping it with Z1. So basically you want to invert some things and then put the homology, Chow homology class or equivariant homology class of these fixed loci. So you have T equivariant cohomology theory of your super stack of stable maps. And you have this localization map. This is a formal way of writing what exactly I said. You don't need to worry that, okay, what's happening? I don't understand this map. You have this, what I'm writing in here is basically saying that we have something like this, okay? So something like that. Tensor CSS inverse, okay? And what is this thing? This is basically saying that if you give me a class here, I can localize it by dividing by Euler class of something. So the whole fraction I would like to think of as still an element in cohomology theory of my ambient world. So it's not numbers that I'm dividing by, it's classes after all. So that's basically what I'm trying to do. So this originally, this is an element of cohomology. This is an element of, okay, so this is an element of homology, but via some duality element of cohomology, right? That's an element of cohomology. So I would like basically to say that you give me a class, I can divide that class by something. So this, you give me a class in here, I would like to be able to divide it by equivariant Euler class of the normal bundle to the reduced space sitting inside this super space. Okay, these are those N1, N2, N3, but here our fixed loci we have shown in our paper are the reduced spaces of Kontsevich. Okay, all right, so S in here, by the way, for sake of completeness, S is a equivariant character, associated to action of T, the torus, on our superstack. Okay, so this is what it is. This localization calculation, before even rigorously can be well defined in the world of mathematicians, was very much, I think, I hope I'm not mistaken, was being used by physicists. So in some sense, a lot of this kind of mathematicians kind of learn from physicists. So physicists do calculations using localizations, one of the major tools of computation for physicists. But anyway, I mentioned to you who are the people who actually rigorously defined it. Fulton and, Atiyah and Bott and Graeber, Ponder, Pandey. Okay. So the super Gromov-Witten invariant, after this long story, associated to these cycles that keep track of where your curve lands inside X, is going to be a modified integral. So like a residue integral. It's an integral, obviously, over the fixed loci of the action of the torus, which are reduced space of Kontsevich. I'm integrating over reduced space. The classes are still there. But now localization construction actually tells me that I can modify these things by dividing by Euler class of these normal bundles. Equivariant, T equivariant Euler class of the normal bundle. Like that. Okay, and again, you actually think of this one as intersection of cohomology and homology classes. So this is this reduced inside super, and you're intersecting it with virtual class 0 and x beta v tau vt, like that. Okay, so that's basically what we are doing here. So compare this with this formula. If you understood what I was basically saying here, this is exactly what we are doing. We are modifying things. Sorry, actually should be here, this part of it, right? So we are intersecting this with some cohomology class. Okay. All right, so this is what it is. And also, there is something that might be worthy of mentioning. So this integral is an integral over the moduli space of a stable map. So basically, so you have this MS, you have the map by forgetting the map phi, like that. And you have, remember you had xn, right? So this was the evaluation map. This was this projection by forgetting the thing, and then you had the reduced spaces sitting inside here, reduced x beta and reduced, only reduced sitting inside here. So one thing you can actually do is you have these alphas that you're multiplying with each other here. You are pulling back something over here and integrating over that space. Now, if you just pull it back and push it forward onto the moduli space of stable curves, so I can pull back this alpha and then push it forward onto the moduli space of a stable curve. This defines for you some element in the cohomology theory of this moduli space of stable curves, rather. And this element in the cohomology theory is actually called Gromov-Witten class. So for the reduced version, you also have it. So basically, you can do the same thing, evaluation, pull back the classes in here, put them here, and then push them forward. It gives you an element of cohomology, and that's called Gromov-Witten class. So this is the super version of Gromov-Witten class. So it's called super Gromov-Witten class. Okay, and it is given by SG x beta of alpha 1 to alpha n, and it is pi over a star of evaluation of a star of this thing. But again, you modify it here because you don't want to do calculations on the super stack, but you want to do calculations on the regular stack. Modify it by taking Euler class of the normal bundle to fixed loci, reduced inside super. Okay. In terms of notations, often when you see the brackets in here, okay, that's the Gromov-Witten invariant. When you see it without the brackets, that's the Gromov-Witten class. Up there, you are looking at a number. Down here, you're looking at the cohomology class. Okay. Any questions?
Yes, I have some questions.
Go ahead.
Okay, the first one is, don't you need actually to do the Gaussian map? Because
Gaussian map, where?
Because to go from the alphas, I mean, one is defining
Correct.
cohomology.
Absolutely.
And
yes, I am being sloppy here. Correct. You need to have Gaussian push forward. So what you do, you pull back cohomologies there, you dualize. You push forward, down there, you will get a homology class, you dualize it again. So you have your map, push forward map involves these two dualizations. And that's right, that's the Gaussian push forward, yes.
Okay, okay. And then the other question is like
Or
above, when you define these Gromov-Witten invariants, you have this interpretation that this is actually the path integral, right? But now in this case where you have this this division over this torus action, so in the path integral, I don't know if you know what is the interpretation of what this
well,
division is.
no, here, well, yeah, so here, maybe what to say, it is also some kind of path integral here, right? Basically, it says instead of, so okay, so these in the case of, for instance, just the Gromov-Witten theory itself, when you have Riemann surface, like you have the Riemann surface, this Riemann surface is your string world sheet, right? So this is the string world sheet. And so often this string world sheet looks like maybe something like this, right? Something like that, or something, maybe it has holes, higher genus. So this is basically the complex curve that you're talking about. And the tip of these things are actually the string. So a string goes from some place to some place, some state to some state. And you're interested in the space of all possible paths the strings traverse. And the paths of the string in the string theory, topological string theory, is given by these Riemann surfaces. Okay, so we have extended this thing to superversion. So you don't have just a path, but you have paths together with functions on them, which are odd variables. So odd fields, fermionic fields. So you're doing bosonic string theory, but together with fermionic string theory. And those fermionic fields they live in some Grassmannian algebra. So you have super curve rather than just a curve. Okay, but that's not important. The point, to answer to your question, is that nevertheless, these curves, these Riemann surfaces or super Riemann surfaces, sits inside ambient variety X. Now, we are looking at all possible ways. So all of these surfaces are paths for us. This calculation tells you that don't count all of the paths. Don't count them. Count less of them. Count the ones which are fixed by the action of the torus. On the space that parameterizes these paths, there's a torus acting. Some of these paths do not change if I act by the torus. If I parameterize the path of Riemann surface inside X, the equation of the Riemann surface is given so that if I modify all the variables by the action of the torus, the equation, zero locus of that equation, still gives me the same thing. Okay, so don't count all Riemann surfaces or super Riemann surfaces. Count the torus fixed ones. There are still paths. But then you would say, well, but I'm counting less. Of course, you're counting less, but you need to correct this error. And dividing by this class is the correction. Okay? So in some sense, it is a path formalism, path integral formalism. Yeah. But your paths are torus invariant, torus fixed. Yeah.
Okay, great. Thank you.
Sure. I have two other questions, just out of curiosity. So are these super Gromov-Witten invariants also rational numbers, or as the usual Gromov-Witten invariants?
Yes. So very, very good question. Yeah, they are rational numbers. Yes, because the reason that you get rational numbers for Gromov-Witten invariants is because it's, roughly speaking, when you count this Riemann surface, you have, by imposing a stability condition on them, you have made sure that this Riemann surface, whether it has genus 0 or 1 or higher genus, always has finite automorphisms. So your moduli space is parameterizing equivalence class of these things. So every point in your moduli stack is that very Riemann surface together with that many copies of it which are related to each other by automorphisms, because those are all isomorphic to it. And your moduli functor is a two-functor fibered in groupoid sections. So all of them are isomorphic. So it actually sees this phenomenon, that it's not just one surface, but it's all isomorphic copies of it. Good. So when you count, the formalism actually naturally gives you how many of those things they are, but you divide by the order of automorphisms. Because you're dividing by some finite number, you get a rational number. That's why you get rational numbers for Gromov-Witten invariants. Up to automorphism, you count one curve, but maybe 3 orders or cardinality group of its automorphisms, let's say 3, 1 over 3. Yeah. And Same thing in here. The reason is because automorphism of the super Riemann surface, super curve embedded into X, is the automorphism of the underlying reduced curve together with extra automorphisms induced by the odd information attached to that curve. One of the odd information attached to that curve is actually very easy thing, a certain parity kind of thing. It's a Z2 action. It's actually swaps two variables and kind of, it's a Z2 action. So it's 2 times automorphism. So yes. So here also you calculate rational numbers for them. But it's not that these rational numbers are just usual Gromov-Witten invariants divided by 2. It's not true, because somehow intersection theory actually tells you that all of these integrals suddenly start showing profoundly different behavior than the usual Gromov-Witten numbers. For instance, I can tell you in some places, you just do certain degree calculations and let's say Gromov-Witten, regular Gromov-Witten invariant vanishes. For us, it doesn't. The reason is because we are doing super phenomenon. So in some places, you'll actually see that all of these classes that I'm defining here, these are super classes. So they belong to cohomology theory, but cohomology theory now is a super version of cohomology theory. So cohomology, Chow homology is actually always stratified, right? It's filtered by dimension, right? Now your dimension are super dimensions. You have even and odd dimensions. So you could have things which are non-vanishing because their even and odd dimensions are matched with each other, even though in the regular version they might vanish. So that we saw some kind of phenomenon that our Gromov invariants do vanish, these things don't vanish, or there are certain relations between these super Gromov-Witten invariants. We don't understand them, but they exist. But the Gromov-Witten invariants do not have those relations.
Okay, okay. And
yeah.
My second question is if there is also an equivalent super version of this Gopa-Kumar-Baffa invariants, and if they are related with the super Gromov-Witten?
So good question. No, it doesn't exist. It's very, very, very highly difficult to actually define super Donaldson-Thomas invariants or super Gopa-Kumar-Baffa invariants. This question that you asked is a very brilliant question, and it's absolutely open. Normally, Gopa-Kumar-Baffa invariants actually are defined, for me, the algebraic geometer who doesn't know physics, for me, it's actually defined as certain sheaf invariants. Okay, so the moduli space of coherent sheaves over super varieties is absolutely not well studied, especially the sheaves that we are interested in. For instance, in the story of Donaldson and Thomas, of course, Richard Thomas defined moduli space of all coherent sheaves, but one immediate application of that was that if your coherent sheaf is an ideal sheaf of a curve, so that's a sheaf of functions vanishing on a curve. Well, if you look at functions vanishing on curve and count them, it's the same as counting themselves. That's why this Gromov-Witten Donaldson-Thomas correspondence became very popular after this. Okay, the moduli space of ideal sheaves of functions vanishing on curves is a Hilbert scheme. It's the Hilbert scheme of curves. And Donaldson-Thomas invariant in that context will be some kind of integral over the virtual class of the Hilbert scheme, basically. Okay, the super Hilbert scheme is absolutely not well studied, let alone doing intersection theory on it. Good question. I've been okay. So I can tell you at least historically something that I always value. First of all, I should say that I would like to mention the name of the amazing mathematician who passed away, Professor Manin, Yuri Ivanovich Manin. Such an incredible person. All of my teachers have been incredible, but he was amazing, just amazing to me. Admirable person to me. And he's the one who actually told me. So he is the only one, if you search, he did push supergeometry for a long time in the math community. And he's pursuing pursuing definition of super Gromov-Witten and super Dawson-Thomas theory. Now, I would like to point out that, of course, this was an amazing suggestion, but the reason it didn't work out is because exactly when you do intersection theory, as you realize, you're doing intersection theory in Chow homology. Without having a super version of Chow homology, you cannot do intersection theory. Okay, so everything needs to be supersized in order to work out this calculation. And as you can see, even though our construction kind of a priori does depend on left-hand side of this equation, meaning this virtual cycle being an element of superchromology, we don't take anything of that. We actually, everything on the right-hand side of the equation is the cycles, homology and homology classes of the fixed loci, which are the regular stable map moduli spaces with a well-defined homology theory. Okay, so only in terms of, with regards to definition, the left-hand side just recently has been defined. Okay, so in any case, I must say that constructing this theory for Dawson-Thomas and Gopal-Kumar-Vafa has to do with studying the super Hilbert scheme of curves and moduli space of super sheaves associated to it, and I think it's very, very difficult. No one has done it, I don't think, but that's a very good question, actually. Very curious, very nice project, that would be. So let me see, I'm almost 10 minutes, right? Am I right, Daniel?
Yes, 12.
Okay, so maybe I just mention something. So you kind of know what the super Gromov-Witten invariant is. So let me just say something about this normal bundle. Okay, so I think if you're a curious person, you will say, okay, the integral over here is over regular reduced moduli space of a stable map. So that is okay. That's very nice. I know what that is. The only thing I need to be curious about and kind of figure out what it is this part. Everything else is an intersection homology on the regular concept, which is a stable mass. So that's the only thing that you need to figure out in order to finish this calculation without really using any intersection theory on the super stack. So maybe I just say something about this normal sheaf a little bit. Some detail in 10 minutes, some detail on N M reduced inside M super, this normal sheaf. It's called, by the way, this thing is called supersymmetric. Supersymmetric normal bundle. Okay, unmoduli space. Space of stable maps or super stable. Moduli space of super stable maps. Okay, so what it is, to define it, let me say the following very quickly. A pre-stable curve over a base S is a flat, proper morphism. Its bundle is over loci of the moduli space. I need to define what this bundle is. Loci of moduli space are families, right? A point of the moduli space is one curve. Already a one-dimensional locus in the moduli space is a one-dimensional family of the curves, right? So I need to basically tell you what this bundle over families look like. So it's a proper morphism C to S such that each geometric fiber is reduced. One-dimensional scheme with at most nodal singularities. So this is a family, a sublocus of the moduli space. The whole ginormous moduli space. If you stand somewhere, you're looking at one of these curves mapped to X. If you walk on a path, on a straight line, That's already a one parameter family of those curves, right? So you're looking at some map from some scheme over parameterizing the space S. For you, the parameterizing space is the line on which you're walking. And every fiber of this family over that space, over every point of the space, you are hitting a curve. So the reduced geometric fibers are your nodal curves, okay? That's what the family is. And let I be a finite set of cardinality n, and I marked pre-stable curve, over a basis scheme, In my example, the basis scheme for you is the line on which you're walking. Over a basis scheme S is a family, C over S, together with functions or sections, I'm going to call it PI, from the base of the family to this family itself for I in I, such that, and I'm going to draw a picture for you, such that in each geometric fiber, the image of sections, Daniel's picture keeps obstructing me. Image of sections are distinct points lying on a smooth. These are absolutely very important for this construction, on a smooth locus of the family. Okay, so let's have a look. So I have a family of curves. I'm walking on this path S in my moduli space. I'm looking at a family, total space of this family is some screen like this. For every point of my path, the S, I'm looking at a curve with nodal singularities possibly, and with some markings, P1, P2, maybe Pn. I go somewhere else. Well, the curve can exhibit deformations. So walking in the moduli space associates to deforming the curve. So your curve might become something like that, P1. Number of mark points doesn't change on it, but the curve changes, nature. And some of these things are actually smooth too. P1, P2, Pn, right? Okay. And so when I say that we are looking at these markings as sections, really, is because you look at it, if you make sure that these markings are always lying, you see, the markings cannot be somewhere there. Marking is not supposed to be a singular point of that curve. It should be always a smooth locus of that curve. And the markings cannot lie on top of each other. They should be always distinct. They are, then they provide for you, you can connect them, you can connect all the P1s, and you can connect all the P2s, and you see you will get isomorphic copies of the base S into the family. And those are the sections. So this is your family, and these are your sections, right? So this is the section associated to PI. So this is P1 section, this is P2 section, Pn section. It's the locus of connecting all the P1s in the family. Okay, now an S-flat family of stable curves is a flat family over S as above, where the fibers are stable. So they satisfy stability of the curves. So all the fibers, these curves have finite automorphisms. Okay, and so now that you have make sure that these have finite automorphisms, you can associate to these things the graph, which the tree, you can have the graph. And similarly, you can have notion of families of curves over this S base S with fixed graph type or with fixed tree type. So why is this important? Because in fact, as you fix this tree type, all of your fibers, geometric fibers, have fixed tree type. That actually gives you a way of defining what this normal bundle is. So associated to this family, see, there is a spinor bundle. It's the square root of the canonical bundle. So fiber of it over every member of the family is the spinor bundle on that curve. So this is your family of curves. Family. Okay, so this thing itself is fibered over S, right? It's a flat family, and there is some S on it. Okay, and then basically, let's call this one pi. S2, so C is pi of S, like that. So C is going to, okay, so like this, and then, okay, I don't need to actually do it. And then here, actually, you will get a short exact sequence the following way. So you have pi of S upper star of S, let's call it C, S of C, okay, goes to sum of nodes and markings. So let's just say Q. So nodes are, I'm going to have also nodes here. So these are QIs. Q, for instance, QI. So these also. So you see, it might be that the smooth curve deforms into a singular one, in which case the node disappears. When I fix the tree type, this phenomenon does not happen. Either there is no node at all, or if there is, it's gonna stay. So basically something like this. So I will change my picture. So QI, something like that. And then these also define sections. As soon as you fix the tree type, these also define sections like this. And okay, I'm almost done. So this would be S, let's say, let's call it Q, the section Q. Okay, how do I delete this? Okay, Q star of S of C plus sum over all pi star of S of C. And the co-kernel of this is this normal bundle, C to S. Let's just put it like this, normal bundle of the reduced family with regards to the superfamily, and it goes to 0. Okay, so what is it we are doing? You have these sections. Okay, sections, PIs, are defining maps from S to the family. If you have a bundle over this family, let's say a spinor bundle of the family, you can map it to PI upper star of that bundle, and that would be a bundle on S. Similarly, if you fix the tree type, QIs, the nodes, you have markings and the nodes, and markings and the nodes are separate from each other. QIs are also defining for you S to C. If you fix the tree type, this is well defined. Okay, and then you have all still bundle over here, and you can map them QI upper star of SC. So basically, when you sum these things up, and then you have this bundle itself on the map and on the curve mapping it to S, you can see that as a whole, for every sublocus of the moduli space, here is a straight line. You can construct a short exact sequence of bundles. And you can measure exactly what the normal bundle to the reduced curves in the family is when you realize them inside the supercurves or the supermoduli stack. Now, the reason I'm constructing everything over this S is because I want not just S, but I want a normal bundle on the whole space but the space of made of these S's. So if you know how to construct it flatly over S loci, you can construct it globally over the moduli space. Now, I mentioned this short exact sequence is because by construction, this thing does not jump in dimension. Its rank doesn't jump. Rank of this sheaf does not jump at all. So it's this is the reason that when you take the Euler class of this sheaf, not on S, but on the whole loci of moduli space, regular moduli space of stable maps, this Euler class, which is the thing that comes in the denominator, this thing does not jump on dimension. Your alphas are not changing. Your thing in the denominator is not changing. Your virtual class is the virtual fundamental class of Konsevich's moduli space of a stable map. That's not changing. That's why you get an invariant. Okay, so that's why I wanted to mention this caveat here. What is the definition of this normal bundle? It's a very beautiful thing, but anyway, I thought maybe I should briefly kind of mention it to you. And, you know, it's a combination of these spinor bundles. I'm not going to go into detail, but even if you're a differential geometer, you can actually see that the thing that sits in the co-kernel of this short exact sequence precisely captures how the reduced curve deforms inside the ambient moduli stack of supercurves. How the reduced, what's the normal bundle to the reduced locus inside the super locus. Okay. All right, I think, sorry for going over time for 3 minutes, but I think I stop in